Francesc Alted. I work for Continuum Analytics. And during my tutorial, I would like to introduce you to Numbexpr and Cython as libraries that can help you to accelerate operations with NumPy. Okay? Everybody can hear me well? Okay. So for this tutorial, you can grab the exercises, materials in this URL, or these exercises has also been put on the USB key that you have. Okay, so it's just it's a tarball. You have to extract everything, but all the source code is there. Okay, so first of all, I will do some small introduction about the era of big data that we are. Then I will talk a little bit about NumPy and its ecosystem. Then we will proceed with some exercises on Numexpr, which is a library to accelerate, to interpret and accelerate NumPy expressions. Then I will say a few things about Cython, which is a way to compile, which is a language which is very similar to Python, but can be compiled and runs much faster than Python itself. So, of course, we are in the age of big data. There is apparently too much hype on it, but the reality is that yeah, it's true.
Nobody said that so far.
But the truth is that we have, in reality, much more sensors. Computing devices are pervasive. It is really amazing how many information you can transmit by using your smartphones. And it is also true that internet allows to grab data anywhere. And it is really easy to access and to accumulate big data. And of course, meaning all that big data has a lot of benefits because you can extract a lot of value from meaning this data. But however, the problem is that the bigger the data is, of course, the slower we can process it. It's just a matter of fact. So processing this data faster gives us more chances to get insight behind it. So our challenge is that we must use our computational resources optimally in order to be able to get the most out of big data. And NumPy plays a very central role in this aspect because it has become a de facto container for big data applications in the Python universe. In fact, NumPy has created a very comprehensive ecosystem around it, and there are many libraries that uses NumPy in order to deal with this big data. Okay? There are machine learning libraries, SciPy library, scikit image packages for processing images, stats models, Sage, Pandas, many things. PyCUDA and POpenCL also relies on NumPy in order to accelerate computations. And NumPy has become the de facto standard for good reasons. Okay? It provides a very handy multidimensional data container that allows for efficient data access and also provides powerful weaponry for data handling. And most important is that it provides an efficient in-memory storage. Let me show you an example of how NumPy is much more efficient than the containers that normally provides Python. For example, if we are retrieving data from our relational database and we are using a native Python driver, the way that Python the driver will handle the data to you is that it will return you a list of tuples on every every cell here. It's every element here. It's a cell of the table. Okay. So in order to build all this structure, you need to build an object for every cell, and that results in a lot of overhead. So the NumPy way is to create an structured array here, and there you can put the results or your selections straight in memory. So as a result, you have faster creation time because it is much faster to create one single object that creates many objects. You don't have memory fragmentation, which is essential when you want to optimize your access to data. And in this way, you have only 1 data byte normally for 1 data byte in your data means only one byte in memory, okay? While here we have many objects, and normally for the 1 data byte we need several bytes in memory, okay? So this is really interesting, but of course nothing is perfect, and although NumPy is just great for many use cases, it also comes with its own deficiencies. The first one is that, unfortunately, NumPy is enforced to follow the Python way to evaluate expressions. For example, if you are evaluating A by B plus C, you first need a temporary, okay, to host this information, and then add the C array here. I will explain that why this is a problem more in detail in a few minutes. And the second thing is that NumPy doesn't have support for multiprocessors right off the box, except if you use BLAS computations and you linked your NumPy with a BLAS that supports multiprocessing. Okay, but in general, NumPy doesn't have this multiprocessor support. So here is where Numexpr can help, okay? Because Numexpr is a Python library which is geared to deal with complex expressions. So what Numexpr has, it comes with a specialized virtual machine that evaluates expressions, okay? It also wears a just-in-time compiler that can compile these expressions for this virtual machine. It accelerates computations mainly by making more memory efficient usage, as we will see, and it also has support for extremely easy to use multithreading, as we will see too. Which by the way, is active by default. So you don't have to do anything in order to access this capability. So for example, let's suppose, just to make a simple example, that we want to evaluate this polynomial in the range -1, 1, with a step size of 2 by 10 to -7, using both NumPy and Numexpr. Okay? So if we do that, and in order to compare peers with peers and apples with apples, we should be sure that Numexpr only use 1 thread, because NumPy only uses 1 thread by default. Okay? So the exercise must be carried out with this. Okay, so let's enter into my Python console. And first of all, let's create the x-axis, the points for evaluating the polynomial. Oh, I think, sorry. I need to enter in PyLab mode. Yeah. Oh, the comma, yeah. Okay. And now we just evaluate the polynomial. So this is the way that, can everybody see the text? Let me. Oh. Okay. So here we can we already done this computation using NumPy or the polynomial, and we should, if we measure the time that the computation takes, we can see this 1 second and 18 milliseconds. Okay. So if we use, let's try with Numexpr. So just import the Numexpr library as NE, and then let's do the same computation using Numexpr. Evaluating this expression is as easy as convert the expression into a string form. Okay. And just let's make sure that the result is the same than in NumPy. So let's make use of all clause. Okay, so all the results are the same. So we have evaluated the same expressions, exactly the same thing. And let me show you the time that Numexpr takes for doing this.
So that was with a single thread?
Yeah, exactly. We need to make sure that we are only using one thread. Thank you. So here is 2 because it returns the number of threads that it was using by default before. Okay? So okay. So Numexpr takes only 20 centiseconds. Okay. And if we remember the time that it takes to NumPy to evaluate the same thing, it is almost 6 times, almost 6 times more time than Numexpr. So Numexpr can evaluate these sort of things much faster than NumPy can. Okay, so that's a nice thing, but what happens if we express this polynomial in a better way? This is the factorized version of the same polynomial, and we redo the computations. So if we do that, this is the short version of the polynomial, the factorized version. Okay, so it takes just half the time than the original expression. Can anybody explain why this is so? What do you think? We are using just NumPy here and here. Why this expression is twice as slower than this one? Less number of operations. That's a possibility, but this is not the reason. In fact, this operates with less. This takes less operations to carry out, but this is not the reason. Another suggestion, or at least is not the main reason. it's a reason, but it's not the main one. No. No. These are possibilities that contributes, but it's not the main reason. The main reason is that in this expression, you are using x power to 3, okay? And this is executed calling the cpow function in the C library, okay? The pow function is called transcendental. So it cannot be evaluated in one single clock as, for example, a multiplication or a sum. Okay? It takes tens of cycles, CPU cycles, in order to evaluate that. Okay? So one first thing that Numexpr does in order to optimize the evaluation of expressions, well, here it is the time. We can see this expression here, the original version. And one measure that Numex does is that Numex analyzes in the flight this expression and can can expand these pow things into a series of multiplications. Okay, so this, in this example, this multiplication takes only 3 clock cycles, or two clock cycles, okay? Because one multiplication can be done in one single clock cycle. And in this case, NumPy is calling pow that can take tens of more clock cycles. So this is the first one of the reasons why Numexpr is performing much better in this case. However, in this case, we don't have this expansion, and Numexpr and NumPy are executing exactly the same thing. Okay? However, Numexpr can do much better than NumPy. And in this case, you are right, there are some temporary things, some temporary objects that are making this evaluation slower. So let me explain why NumPy is so slow in this case. Well, so Numex is executing this expression 3 times faster, around 3 times faster than NumPy. So the short answer is that it can do that because it makes a much more efficient use of memory resource. So this is the short answer, but in order to explain the things in detail, let me tell you about the CPU starvation problem that most of our current CPUs are suffering. So the thing is that currently CPUs are typically stay bored, okay, and doing nothing most of the time. So this is because they are waiting for data. You may have the fastest CPU in the world, but if your memory subsystem is not fast enough to fit it, they are staying doing nothing. So this is a graph on how the speed of memory in red has been evolving through the time in nanoseconds, okay, from 1982 till 2007, Okay? And in green, we see the speed on how the CPU speed has been evolving. So it is evident that the two speeds are being drift a lot through the time. Okay. So this is and with the age of multicore in blue, this difference is still growing more. The problem with the mismatch between memory cache between memory and CPU is so apparent nowadays that people is writing complete books about the problem. Okay. So this book appeared 3 years ago, and I think the title is explicit enough. It's the memory system. You can't avoid it. You can't ignore it. You can't fake it. Okay. So in order to get the most out of your computers, you need to understand how this memory system works. So this is how things are now. Memory latencies are much slower, between 250 times and 500 times slower than processors. That's a lot. Okay? And memory bandwidth is improving at a better rate than memory latency. However, it is still much slower than processors. And it's between 30 times and 100 times slower. So in order to cope with this problem, what vendors are doing is to introduce caches in CPUs. Okay? So the idea on the cache is that the caches in CPUs has much less latency and throughput, and are much better. The latency and throughput are much better than main memory. However, the faster the caches run, the smaller they must be. This is why. This is because of heat dissipation, power dissipation problems. Okay? You cannot put a lot of memory inside of a CPU and make it run very fast, because they dissipate a lot of heat. So this is the evolution of the CPU cache through the years. Okay? Originally, we only had a CPU, main memory, and mechanical disks. Okay? This architecture is very simple to understand, and it's relatively easy to make an efficient use of memory. In the 90s and 2000s, we have seen the vendors were implementing this kind of architecture. In the CPUs, it appeared a level 1 cache, and then a second level cache. Okay? Then the main memory, and then the disks. And we will be seeing during this decade is that in CPUs will wear 3 levels of cache, main memory, and another layer, which is solid-state disks, that in many cases will act as a cache of mechanical disks. Okay? So we must be aware of this kind of architectures if we want to get the most of our architectures, of our computers now. And this is not easy. So in order to actually improve our speed, we need to understand in which cases CPU caches are effective. And they are effective mainly in a couple of scenarios. The first one is when there is time locality. So this is when basically a data set, or a small part of a data set, is being reused. And the second one is when there is a spatial locality. That means that the data set is accessed sequentially. Okay, so for the time locality, realize that you have an C array in memory here, and you are accessing these 4 elements repeatedly through the time. Okay? So the first time that the CPU needs these elements, the system has to fetch the elements from the memory. But the second time, the elements has been transmitted to the cache, and the CPU only needs to fetch them from the cache. Okay? So this is the time locality. And the spatial locality is when a data set is accessed sequentially. Okay? So in modern systems, when you have, for example, an array, there are directions where you can retrieve data much more faster than the other directions. And the direction that you can retrieve data faster is when the data is contiguous. Okay? This is because of how memory subsystems are designed. So in this case, for example, when the CPU needs to fetch this row here, the first time that it accesses this element, the contiguous elements are being transferred automatically to the cache. So the second time, it will get the elements from the cache, not from memory. And also modern systems has a special hardware to detect access patterns. So if the CPU detects that you will be accessing elements in this direction, he will download or prefetch these elements here into the cache. So the CPU will retrieve the elements from the cache, okay, not from memory. Of course, this doesn't work if you are accessing elements in this direction, for example. This is not a good way to travel data, or just in random order. Okay. So these are the 2 ways: time locality and space locality. And there is a simple technique that ensures you that you can access, you can make an efficient use of your caches. That is called the blocking technique. The blocking technique is very easy to understand. It's just, for example, if you have 2 data sets in memory and you want to do an operation with the data sets, the blocking technique says, well, just transfer blocks, contiguous blocks, okay, into your data sets, transfer them to the caches, do all the operations in cache because it is faster, and when you have the result, copy the result to the data set in memory after them. Okay? And while these blocks are in cache, reuse them as much as you can in order to make advantage of the time locality. Okay? So this technique is basically what Numexpr does. Okay? So this explains why Numexpr is still faster in this situation. So for example, for NumPy, we have to compute this expression here, a by b plus c. NumPy will need to first compute this multiplication, and we'll need to create this temporary in memory, completely in memory, okay? And then use this temporary and sum to this one to create the final result in memory. So the thing is that NumPy needs to put much more memory. These temporaries are traveling to memory, and this takes a lot of time in modern systems. Okay? On his hand, what Numexpr does is to apply the blocking technique. Okay? It transfers blocks, small blocks of the operands to the cache. It does all the operations in cache, of course with temporaries, with everything, but the temporaries also fits in cache, that's important, and then put the result on the final destination. Okay? So you completely avoid the creation of big temporaries in memory, which is slowing down many NumPy operations nowadays. Is that clear? Okay. So you don't need to use Numexpr in order to use the blocking technique. For example, this snip that has been contributed by Stefan, it's using also the blocking technique for evaluating the polynomial, but using pure NumPy. Okay, it only uses, it makes a loop, and it fetches blocks from the X, and they then do all the operations in place. Okay. So this is how to do the same thing in NumPy. And you can see that if we represent the block size here in terms of the execution time, we can see here that we have a minimum time here. Okay? What do you think this minimum represents? The size of the cache. Okay? So when the block size fits in cache, everything runs fast. Whenever the block size runs out of the cache, your time to take the computations increase because of memory bandwidth, not because of we are doing more computations. Okay? The thing is that many times implementing this blocking in NumPy is quite inconvenient. Okay? And Numexpr can do that for you automatically. And the second reason for not using this is that NumPy also have some overhead from fetching views and doing all these kind of things in Python space. Numexpr is doing the same thing in C space, so it's running much faster. Yeah, this is because of in the beginning there is overhead. So when the block size is very small, this loop is much longer. Okay, so you have to do much more iterations, and there is an overhead of creating views in NumPy. Okay, so this part is just a consequence of this overhead. Here, there is a good balance between the overhead of NumPy and the block sizes, and here you have block sizes that exceeds the CPU size, the CPU cache size. Yeah. Okay. Another interesting thing of Numexpr is that I don't know which time is it. Okay. Is that it can make use of multi-cores automatically. That's a really interesting thing. And you can do that automatically. And you can even select dynamically the number of threads that you want to run in order to evaluate your expressions. So let's make an exercise. Let's put the number of threads for evaluating this expression to 2, which is the number of cores that I have in my laptop, and just redo the computation by using Numexpr. Okay, so by using 2 threads, let's switch to 1 just to see the difference. By using 1 thread, the time is 17 centiseconds, and by using 2 threads, it's 11. Okay, so it's very easy to use. So it's just a matter to select the number of threads that you want to run.
And that number is set by number of processors?
By default, this number is the number of processors that you have in your system. Yes. Yes. It detects automatically the number of cores that you have in your processor, and it uses all of them. But you can select the number you want automatically. Okay, so let's have a look at a machine that has 16 cores, and just to see how the efficiency scales. In blue, there is the non-optimized version of the polynomial. In red, we see the optimized version of the polynomial. And in yellow, there is an interesting thing. There is only, the polynomial is just an x. That means that we are doing just a copy operation. We are not computing anything. Just we are doing a copy of vector x to vector y. Okay? So we can see that the performance, the speed up is quite good. It can be around 4 times faster to run on all the 16 CPUs. Okay? And for the optimized version of the polynomial, the times are better, but when we have many CPUs, the difference of time is not that much. That means that for Numexpr, you don't really mind too much if you use an optimized version of of your expressions or not. Numexpr is normally able to manage your complexity for you. Okay? And an interesting thing is that when you're doing not operations at all, Numexpr is able to reach almost the performance than if you are not doing operations at all. That is because, in this case, the bottleneck is memory access. It's not CPU. Okay? So Numexpr allows you to get almost perfect or allows you to reach performance that is limited by CPU, by memory bandwidth operations. This is a comparison of Numexpr with a very well optimized C version of the same thing by using OpenMP. OpenMP is a specification that allows you to annotate your C code in order to produce parallel code automatically, and it is supported by most of the modern compilers. Okay, let's have a look at how this works. So this is the C version of the polynomial evaluation. This is the interesting thing. This is the loop where the polynomial is being computed. And OpenMP is just as easy, using OpenMP is just as easy as adding this annotation here with the pragma, OMP, parallel, and you declare that the I index, this loop can be parallelized. Okay? And you can also specify the schedule. If the OpenMP will do an static partition of your job, or will do a dynamic partition. In this case, we have used a static partition because it is the most efficient one. So this is how the OpenMP works. And we can see here, so this is the fastest performance that you can get from this system. You can see that Numexpr it's around only twice as slower than the best way to compute this polynomial. Okay? This is a very interesting thing because you know that Numexpr is interpreted and this code is compiled. Okay? So without any effort or very little effort, Numexpr can help you to accelerate your computations. Here is a comparison with a version of C of OpenMP in C, which is doing only a memory copy. Okay, and we can see that the performance is very similar than evaluating the polynomial. This is because this problem is basically memory bandwidth bounded. For problems that are not memory bandwidth bounded, for example, computing transcendental functions like the sine or cosine, the scalability of Numexpr is much better, okay? Because you don't have this bandwidth limitation. You are using your cores much more effectively. But still, yes. And you can see here also an interesting thing is that this machine doesn't have 16 physical cores. It only has 8 physical cores, and the rest of the cores are logical. This machine is using Intel hyperthreading. Okay, so these logical cores here are these hyperthreaded ones, but we can see that after the 8, the speed that hyperthreading can give us is around 30%. Can give us a 30% better speed. So hyperthreading is not only hype, it works. Okay? 30% is not that bad. Okay, so but Numexpr also has limitations. And for example, Numexpr, one of the limitations is that Numexpr only implements element-wise operations. Okay, so it can only deal with expressions where you can do operations element by element, but using always the same index between the vectors, okay, or matrices. In particular, you cannot do this sort of things by using Numexpr. For example, we are using an index, a different index here than in the same iteration of the loop. We are using index I, but index I minus 1. So these sort of things cannot be done with Numexpr. Okay. So this is where Cython can help. Okay. And this is the second part of the tutorial. And Cython is a language that is very similar in syntax to Python, as we will see. It generates C extensions, so it is compiled. It is not interpreted. But, and the most important capability of Cython is that it is very easy to access both C and Python libraries from it. And it's very useful for gluing C libraries with Cython. In addition, it integrates very well with NumPy, as we will see too, and also has support for multicores right on the language. This capability has been implemented in the past August. It's really important, and we are going to exercise that too. So, if you want to go to the exercises Cython poly directory, you will see an example of performing okay, I think I have problems. Can you see the code? Yes. So this is a sample, an example of Cython code. The syntax is very similar to Python. Okay. You only have different things. For example, this C import thing doesn't exist in Python, but that means that this NumPy library has to be imported in order in C space in order to get access to the C API of NumPy. Then another difference is that this cdef function means that it can be only called from C space. In that case, from Cython space, not from Python space. Okay. And you can also type the result, the outcome of your functions, and also the types of the parameters. So it's a kind of a mix of C but with the syntax of Cython. In that case, we evaluate the polynomial here, and we declare another function, which is called poly, that takes a couple of parameters here. This is a function, it is def, it's not cdef. That means that this function can be called extract from Python directly. Okay? And these two parameters, the types of these two parameters are pure ND arrays. That means that from Python you can pass these arguments as NumPy arrays, and you can manipulate here the arrays much more efficiently by declaring that they are ND arrays. Okay. So let me show you how this is called from Python space. From Python space, it's just a matter of importing the poly, which is the extension that has been generated by the Cython sources that we have seen. We generate this vector, x vector, and we generate an empty container for the outcome of the polynomial computation. Okay, and then the only thing we need to do is to call the poly function that is this part of the poly C extension, and we pass the x, which is a NumPy array, and the y, which is another NumPy array. That's all. Okay, this is the way you can access to the C extension that is created by this code. Okay, so let's run it, and let's see how it can accelerate this sort of computations. So let me show you very, very briefly how to compile, how to create a setup.py in order to create the extension. So the only thing is to import these two tils and then declare that we are going to build an extension. Okay? The source code is here, poly.pyx, and you can pass different compile arguments. This is for the parallel version that we'll be seeing soon. And then adding some meta information to the package. That's very easy to create this. And then to create the extension is just a matter of using the these2tils package in order to create. Set up the build extension in place. This flag means that we want the extension to be in the directory, in the working directory. So okay, Cython has created a C file out of the source file, and then it compiles the result with GCC. And it creates a library here, a C extension. So if we run the result using our script, we can see the result here. Okay. So Cython allows to run this in 45 centiseconds, which curiously is much more time than it takes Numexpr. So something is going wrong, because in general with Cython you can get much more speed than with Numexpr. So let's have a look at how we can optimize our Cython code. For this, Cython provides a nice tool, which is a way to annotate your code. So if you use Cython minus A, you have, this will produce an HTML file, which is the annotated version of this one. Let's open this annotated version in our browser. Okay, it's here. Let me reload this. Okay. So in the annotated version, the line is, the darker the yellow is, the most operations needs to complete. Okay. So we must focus on very dark yellow lines in order to optimize our code. Okay. For example, here we have a, if you click on this line, you can see the output that Cython is creating for this line. And this output is in C. Okay? So we have a lot of things here, but we cannot do very much about optimizing this. Okay? But let's focus on these yellow lines here. Okay, this is a simple assignment here. xi equals the I element of the x vector. Okay, and it is creating a lot of overhead, Python overhead, calling pyfloat from double conversions. So this thing is being executed mostly in Python space, because it is calling Python API, Python functions. So here's the same thing, and here too. So how we can optimize that? Well, let's have a look at another version, which is called polystatic, and let's see how it differs from our current version. Okay, so these changes are not important. The important changes are here. Okay, this version adds static typing of several variables in our loops. That's really critical if we want to get the most performance in our Cython files. So let's copy this file here. And let's have a look. No. Okay, so by declaring this variable here, I, vlen, and xy, xi, and ya, we can see that we are specifying to Cython that these variables are longs and are doubles. Okay, so Cython with this information can create much more optimized C code. Let's have a look at the new code that Cython generates. We create the annotated version. This is the old version, and if I do a reload, we can see how these two lines here that has been represented in yellow now are turned to white. Okay? That means that these lines doesn't expand to Python code. It only expands to C code. Okay? So they are much more efficient. As these lines are in the middle of a loop, the boost can be important. So let's compile again with a new version, and now run it. So from, I think it was 45 before, just by doing this static typing, the time has decreased by a factor of 3, which is really, really, really interesting. Okay? So, and in fact, this number is very close to what Numexpr is doing. In fact, it is better this time than Numexpr using only one CPU. Okay? So let's go with how to parallelize this code with Cython too. Doing this in Cython is also quite easy. So this is the parallel version of the same code, and we import here a special feature which is called prange. Prange is the standard way to parallelize loops in Cython. Okay. So, and here we have added another flag to this function, which is called noGIL. How many of you knows about GIL? What GIL is? Okay, so most of you. For those that you don't know, GIL stands for Global Interpreted Log. Okay, so it's well, some call it a feature, some call it a bug, but it's a log that is implemented in Python that prevents from several threads to run in parallel. Okay. So this is a common limitation of Python applications that they have to fight with the GIL in general. So the way that Cython has to fight with GIL is with the GIL is that he can release the GIL can be released when calculations are being done in C space, not in Python space. So Cython can generate C code. So this is one of the reasons Cython can get rid of the GIL. So this is a way to specify, hey, my function will not need the GIL. So please generates code that doesn't depend on the GIL. But here it's just a declarative thing. Where the GIL is actually released is here. So this was before for I in range, okay? And now, by using prange, we have to make sure that we put this no-GIL parameter to true. So we are telling to Cython here that we want to release the GIL when we are performing the loops in this computation. Okay, and also you can select the schedule to be dynamic or static, because this implementation of parallelism in Cython is based on OpenMP, as we have seen before. Okay. So let's make use of this new version of the parallel. Let's copy this. And execute, compile, okay, and then run. This way, this time, we will run in the parallel version of the polynomial of the computation, and we can see that, well, my laptop only has two CPUs, but we were able to see a good speed up from 12 to 9 centiseconds, which is really nice. So here we have a plot where we can see the speed ups that can be achieved by using the parallel version of our code by using Cython. Okay. Curiously enough, here is a bump that when using hyperthreading, it seems that the performance degrades. I don't know exactly why this is, but well, this is the results that I get. But in general, this performance seems better. Well, this is a comparison between, I don't know if I have time to explain it. Yeah, maybe. Okay, so we also have seen that Cython provides a way to distribute the job differently. This is not. To distribute the job among the different CPUs, okay? By default, it uses, I think, in fact, the OpenMP doesn't specify what the default is, but most of the platforms use the static partition of the jobs. But you can also specify a dynamic partition of the jobs. Dynamic partition means that instead of splitting your data domain in even partitions, the dynamic thing means that it splits only uses a few partitions first, send the partitions to the CPUs, get the results back, and whenever when a core has finished with his job, the master will send another job to the CPU. Okay, so it has to wait until the job has done. And the static partition means that everything has the same size, your range domain, and it is sent to every CPU one after the other. Okay, so this has more overhead because it implies some handshake, and we can see here that for the polynomial computations, the static partition works much more efficiently than using a dynamic one. Okay, but this is not always the case, because, for example, for doing a computation of the Mandelbrot set, as many of you will know, computing this black pixels here takes much more time than computing the blue ones. Okay. So if we apply the different schedulers to this problem, we can see that the dynamic partition scales much better than the static one. Okay. This is because the time that it takes to compute the pixels is not always the same. So a dynamic partition, in general, is better. You can see the C code for this evaluation also in the exercises table. Okay, so to conclude, let's see how the parallel implementation of Cython can compare with the pure C OpenMP version. Okay. So the parallel version of Cython is in blue, and the C OpenMP is in red. Okay. So for one processor, Cython has some overhead, but this overhead reduces as we are using more processors, as we are throwing more processors into the computation. Okay. And in fact, for 8, the time is more or less the same. Even for 7, the time is exactly the same than using the pure OpenMP C version. So that means that with Cython, you can actually get all the performance from your applications. Okay, that's really interesting. And we just for curiosity, the OpenMP version of doing the copy, doing this one, the performance is exactly the same than using. Well, we already have seen this result. Okay, that evaluating the polynomial is the same thing. It takes the same time than just copying the x vector to y. This is exactly the same plot, but instead of representing times in this axis, I have represented memory bandwidth. Okay, so this is a really interesting plot because we see that when we reach a number of CPUs, we are mainly limited by the memory bandwidth of this machine. The memory bandwidth of this machine is around 16 gigabytes per second. Okay, so we can see that adding more CPUs is not going to speed up our computations, because for this particular problem, this machine is already delivering all the bandwidth it can provide. Mm-hmm. And yeah, so that's interesting. Yeah, I understand. Exactly. You have here in X there is 10 million elements, which are double precision, and here you have also 10 million. So I sum the both, and I get the work set size. I just divide by the time. And here it is a final comparison among Numexpr in blue, Cython parallel in red, and C OpenMP in yellow. Okay, Numexpr is the lowest, consistently the slowest. But the advantage of Numexpr, as I said before, is that it is interpreted. Okay, so you don't need the compile step in order to get these speeds. Then, when you absolutely want the highest speed, the best thing to use is Cython parallel, because you can reach more or less the same speed than using pure C OpenMP application. Especially if you use a sensible number of CPUs. For example, when you are starting to use more than 4 cores in this example, you are reaching more or less the same speed than a pure C computation. Okay.
So in that case, knowing that, would you restrict the number of threads to 4?
Maybe it's a good idea. For example, here we can see that with 10 threads, we are getting worse results than using, for example, 7 threads. So yes, putting more cores to your application is not always a good idea. So it's always nice to do some benchmarks, because maybe there is an optimal number of cores that can execute your code more efficiently. So it's always a nice thing to do some benchmarks and explore which is your ideal number of cores for your computations. Yeah, good question. The reason is when you put, most of modern computers are memory bandwidth limited. When you put a lot of cores trying to access memory at the same time, you are pushing a lot of pressure on your memory system, sub-memory system. Okay, so in many use cases, it is better to reduce the number of cores that are accessing, are doing pressure on your memory subsystem. Okay, and this is why you could get this sort of things. Another important thing that you may want to see here is that this is just a copy. Okay, I don't know exactly how this is implemented in at hardware level, but one interesting thing is that a single copy can be more efficient if you use more CPUs. This is a striking result, because you don't expect initially a MIMCPY going faster if you use more cores than one. In principle, what you expect is to reach the highest performance by using one MIMCPY call. Okay, you expect that, but the reality is that I consistently get this kind of speed ups in copy operations when I use several CPUs. I don't know the explanation of this. If anyone can bring some light here, I will be grateful. You understand the problem? I don't know. Anyway, and of course, in my opinion, this dependency of the number of cores in doing the copy is the most important reason why we see speed ups when doing memory bandwidth bounded operations. These operations is basically memory bandwidth bounded. And this kind of operations are not unusual. The usual operations nowadays are all memory bandwidth. Okay? Memory bandwidth limited. Okay, so that's all that I wanted to say. Just remind that NumPy is de facto container for Python in the big data era, and that NumPy has performance problems when evaluating complex expressions, and that Numexpr and Cython can help to solve this. Numexpr and Cython has different areas of application, but in some areas they can I don't know, overlap. Yes, thank you. So it's up to you which one you want to use. They are both very interesting tools to use. Okay, see, if you are more interested in about the CPU starving problem, I've written an article about this, why modern CPUs are starving and what can be done about it. And for knowing more about Numexpr, there is a nice overview on the website, and using parallelism with Cython it's very well explained also here.